This is Garis MPC, Math, Physics, Computing, 130 plus courses on pure mathematics and mathematical physics. This is course number 4, so MPC 4, on linear algebra, a junior senior level course. This is lecture number 1, session A. We're still in section 2, solving solved problems, and in the previous section we solved part 1 of question 1.27, and now we continue on with part 2 and part 3. Alright, so we're dealing with the dot product of complex vectors and variance. Like here we have a product of a complex vector u times z, and then the whole thing dotted, so dot product with another complex vector v. So in this case we're asked to prove that the dot product of this with v is equal to the dot product of u dot v with a z outside. So in a sense, pulling the z out, outside the bracket. How to prove that? Well, let's start with this. Let's calculate what this is. So zu, now that's just scalar multiplication. So you just multiply each component of your complex vector u by z, so that'll as an n tuple, so this will be zu1, zu2, zun, and therefore if you dot this with v, you will get this. So that's your first vector, and v is your second vector, and it's the dot product, and these two vectors are now complex. So here's the definition of the dot product of complex vectors. So you multiply the ith component of each, and the second term, the second component, don't forget to conjugate it. So you need this bar here, you need to conjugate the second term. Alright, now, so these are just complex numbers, right? And you've got a z in common throughout all the terms in this sum. So it's just a number, so just take it outside the sum. So this z, just bring it outside the sum. So here you've got this. Because you can do that because general form, if you've got complex number times the sum of complex numbers, that's the same thing as the sum of the product. So let's see, the product of the sum equals the sum of the products. So from this you can take the z outside and bring it here. Now let's see. So this equals z times this. Now what is this? Sorry, here. What is this? Well, it's just the dot product of u and v here. So from here we've derived this, and that's what we're asked to prove. So we've proved it. So end of proof mark here. All right, now part 3. So somewhat similar to this, except now the z is here, and the final result is you get z conjugated. So it's a little bit different from here. So when the z is like part of the second term, in a sense, and you bring the z out here, you've got to conjugate it. So let's prove that. Well, so what do we do? We're going to start with the left-hand side. So So this is like your first vector, complex vector, and this is your second complex vector, and you dot product them. So by definition, you have 3 bars here. The dot product is defined as the sum of the product of the components. So the ith component of that will just be ui, and the ith component of this. And now these are complex numbers, so you've got to conjugate that ith component. Now z is just a constant complex number, so it doesn't change. It's the same for each component, and you've got vi here. But this is your second vector, so you've got to conjugate the ith component. So do this. Now, from earlier work, the conjugate of the product is equal to the product of the conjugates. So conjugate that and multiply it by conjugate that. So you get z conjugate, vi conjugate. All right? Now that's a complex number, that's a complex number, that's a complex number. So this number here you can just bring outside the sum. So let's do that. Wait a minute, what am I doing? Oh, I've skipped a step. Okay, these are here. These two complex numbers, your complex numbers commute. So I can swap the order of these two, which I do here. So instead of uiz conjugate, you get z conjugate ui, because complex numbers commute from this form. ZW is wz. Complex numbers commute. Now it's just a complex number, so you can take it outside the sum, which I've done here. And so you're left with z conjugate sum of ui vi conjugate. But this, by definition, is the definition of the dot product of u dot v. And so there it is. There's the right-hand side that you're trying to prove here. So z conjugate u dot v, end of proof sign. All right. Now, the next question is a bit different in style, a new concept. We're introduced to the idea of a directed line segment. So there are 3 ideas there. I'll start with a line. Just imagine a infinite line going infinitely both directions. And a segment is just a piece of it that you cut out. Like imagine, so here's my line, I get my 2 scissors and I just snip, and I cut out a segment, a piece of the line. So this bit of the line. So that is a line segment, right? A piece of the line, P-I-E-C-E. And to make it directed, I make that line segment an arrow. So I could have it pointing that way, or I could have it pointing the opposite way, right? So either of those is a directed, in other words, it has a direction. You've made it into an arrow. So a directed line segment. Now, in ordinary 2D space, you've got to imagine a point P here and another point Q here. So the arrow from P to Q, it's just a line. So it's a line segment, and it's directed. It's pointing either that way or the other way. So it has a direction, and so this arrow vector, if you like, from P to Q is a directed line segment. So that sounds awfully familiar and similar to the definition of a vector, right? It's just as an arrow. Yes, it is. So you can look on vectors as arrow, in the sense of arrows, as directed line segments. All right. Now, so a direct line segment, it's just the arrow from point P to point Q. Now, if you look on P as an n tuple, Now this is supposed to represent an n tuple. Now this is new. It's shorthand. Instead of writing out the n tuple like a1, comma a2, comma dot 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 an, it's a bit tedious. We should just simplify it and shorten it to just simply brackets ai, and it's implied that this is just shorthand for the n tuple. You know, all the n components of r to the n. Okay, so this is just a vector. A real vector in r to the n, n-dimensional real vector space, and similarly for b here. Okay, so point P is a point or a vector or an arrow in n-dimensional space whose coordinates are ai, and similarly for Q, whose coordinates are bi. All right. Now, this directed line so now here I've just sort of made it simple in 2 dimensions, but it's the same concept. You could have this point P in n-dimensional space, and similarly for Q, and the line, straight line, joining or from P to Q, that's your directed line segment here. You represent it in this following form. You write it as these are PQ. You write it as PQ with an arrow above it, and the arrow gives the direction from P to Q. In other words, it's this arrow here, this line, directed line, and line segment. A segment means that, you know, you've got this infinite line going here, but you've just cut out this segment, this piece of the line, and the line is from P to Q, and it's directed because it has a direction. You've made it an arrow from P to Q, and you represent that arrow there, that directed line segment, as PQ with an arrow above it. And since the arrow is going this way, the direction of your line segment is from P to Q. That's the definition. This. Now, think in terms of vectors and vector addition. What is PQ arrow? Well, PQ is the directed line segment, or a vector if you like, from P to the origin, plus the vector from the origin to Q. Now the vector from P to the origin is the negative vector of P. So the vector from the origin to here is vector P. But if you're going the other way, it's the negative vector, so it's minus P. So this vector, or this directed line segment, this arrow, all the same thing, from here to here is the same as adding 2 vectors from P naught plus naught Q. So this vector here is just minus P, and this vector here is Q. So going from here to here and adding to this vector, you'll get here. But that's just the same thing as going from here to here, right? I mean, you could, from the parallelogram rule for adding vectors, you could make your parallelogram, so you have this line here which is parallel to this one, and then and then like this, you had, right? You could do that like that. You draw your parallelogram, and so this vector here is the diagonal of the parallelogram, and by using the parallelogram rule for summing vectors, so this vector PQ is equal to minus P plus Q, or equivalently Q minus P, right? So PQ is you can define it as vector Q minus P, so Q minus P, right? Now, another fairly new idea. Question. This vector here, P to Q, and this vector V, this vector here, V for vector, It is parallel to PQ, and I've tried to make these look parallel, and it's the same length. Right? So V is the same length as PQ. Question: is this vector and this vector, they're both parallel, and they're the same length? Question: are they the same vector? Yes. The answer is yes, by definition. Because what is a vector? You don't care where the vector starts. You don't care where P is. Or for two vectors to be the same, all they need is they have the same direction and the same length, because that's the two essential properties of a vector. What is I mean, from the physicist's point of view, what is a vector? It's just an arrow, so it has a direction and a length. So in other words, this vector V, this vector here, the V, a little wiggle for a vector, this vector is just the same as this one, PQ. So in other words, so PQ by definition is V. So that now since PQ is Q minus P here, this equals Q minus P, that means V is Q minus P. So PQ's V is Q minus P. Now Q is a vector, it's an n-tuple, right? That's here. So now writing it out in full to be a bit more explicit. So Q minus P, now here's your Q n-tuple, your vector. We're in real space, so these are real numbers. Minus P, so here's your n-tuple for the vector P. Okay. Now you're just adding vectors, so you just add the components. So the first component of the sum, in other words PQ, will be B1 minus A1. The second component will be B2 minus A2, and so on. So here it is written here. Okay. So there it is. That's your vector V. This vector here, which is just the same as this one, P to Q, the directed line segment. All right, now let's actually do an example. So part 2 of the question, you're asked to find V, that'll be like this one, when your 2 points, we're now in 3 space, 3 real space, because these vectors have 3 components, real, so these are real numbers, the components of the vector, and you're asked to find the vector V given these 2 points, which these 2 points define your directed line segment. Your directed line segment will be PQ arrow, which is equal to Q minus P. So it'll be Q minus P. So it'll be this vector minus that vector. All right. So here it is written out. So V is Q minus P. So here's your Q here, and there's your P here. All right. Now it's just vector addition. Well, I got a subtraction. So it'll be 6, the first component of V, it'll be 6 minus 1 here, and the second component will be this minus 2, so it'll be 0 minus 2, so that'll just be plus 2, and the third component will be minus 3 minus 4, so it'll be minus 7, and there it is. All right. The next question, last one for now. So question 131. Again, a bit of a new focus, somewhat. We're going to, in fact, we're sort of leading in a bit to an example, concrete example of the topic that we're going to be talking quite a bit about in the next session, which are linear equations and systems, or in other words, a set of linear equations. Now, I won't explain much about what that is until next session, but this is a kind of lead-in, gives you a feel for what's coming for next session. Now, I'll lead into it by giving 2 simple examples, one in 2-dimensional space and a similar example in 3-dimensional space, and then I'll generalize to n-dimensional space. So the equation of a line. So here in 2-dimensional space. So here, like for example, the y-axis, the x-axis, and you have a straight line, an equation of a straight line, and here's your equation of a straight line. So x plus 2y equals 10. And this is the equation of a straight line. Now, why have I put 5 here and 10 here? Well, this straight line, what does it look like? Well, it looks like this. And yeah, it's a straight line. Why? Because these unknowns here, the x and the y, they're to the first power. Equations that involve first power terms, unknowns in first power, they're called, such equations are called linear because they are line-like, linear, the adjective. And that means the powers here are just first powers. There's no x squares or y cubes or anything like that, just to first power. Right, so this line, where does it cross the x-axis? Well, when it crosses the x-axis, y is 0, so the y's drop out, and you're just left with x is 10. So it crosses the x-axis here at 10, x equals 10. So this point here is coordinate 10. And where does it cross the y-axis? Well, when x is 0, so the x here is 0, so you're left with 2y is 10, so y is 5. So the y coordinate is 5, so this point here is 5, the y is 5. And so you've got a straight line, okay? Now, what's the equation for a plane, you know, a flat surface like this in a 3-dimensional space in R3? Well, here's an example of a plane equation, a linear equation. So because these terms here, x, y, and z, they're all first power. Okay, so here's an equation of a plane, you know, a flat surface like that in 3-dimensional space. So you have an x, y, z axis. Now this I can sort of draw it here. This triangle. Now this plane goes on infinitely, right? I've just drawn the part in this upper quadrant. In the where the x, y, and z coordinate are all non-negative, all of them. So here, let's see. that way. Right? So z-axis, x-axis, y-axis. So here's your coordinate frame, and the plane is sort of like that, right? So this is the equation of your plane. Now, where will this plane cut the z-axis? Here. Well, at this point, both x and y are 0, so the x and y drop out, and you're just left with 3z equals 12, so z must be 4. So it cuts this point here at z coordinate 4. Okay. Now a similar question: where does it cut the y-axis? This plane, you know, like that. Where does it cut the y-axis? Well, at the y-axis, the x and the z is 0, so this term and this term drop out, and you're just left with 4y equals 12, so y equals 3. Okay. So this point here is 3. This y coordinate is 3 here. And a similar question, where does this plane cut the x-axis? Well, at the x-axis, the z and the y are 0, so the z and the y are 0, so you're just left with 6x equals 12, so x equals 2. Okay? So that's what the plane looks like in 3-dimensional space, and that's its equation: 6x plus 4y plus 3z equals 12, right? And that was the equation of a line. So it's in 2-dimensional space, So your line is just like a one-dimensional object, and this is in 3D space, 3 space, and this surface here is like a two-dimensional object, a two-dimensional thing, and a flat surface. That's what a plane is. All right, now let's generalize. Now we'll go to n dimensions, and an n-dimensional plane has a special word for it. It's called a hyper. Hyper just means above, like means more dimensions, above the usual 3 dimensions. So a hyperplane, that's in n dimensions, and its equation, now like here's equation for a line, here's an equation for a flat surface, a plane in 3 space. So what will the equation look like if you generalize for a hyperplane in n-dimensional space? It'll be like this. So here you got like constant, and a variable or unknown, variable. So generalize to n dimensions. So you'll have n constants, and you'll have n unknowns or variables. So x1, x2, ... xn. Okay, and equal some constant here. Like here it was 12, here it was 10. Okay, so this is just a n-dimensional generalization of the 2D case and the 3D case. Okay. Now, any set of values for these x's, if you plug them in to this equation and the result is b, then that set of values, x1, x2, ... that n tuple, that's said to be a solution of this equation. Now, this is a surface in n-dimensional space, so there'll be an infinite number of uncountable number, infinite number of points on that space. Like take the 3-dimensional case. So you've got this hyperplane. How many points on that space, on that plane? Well, infinite number. You can't even count them, right? It's a uncountably infinite number of points on the space. Those points, they are lying on the space. They are said to be solutions to this equation. They are n tuples, x1, x2, ... and there will be an infinite number of these n tuples lying on the space, right? And those n tuples that lie in the space that are solutions to this equation, if they lie in the space, then they're if they lie in the plane, if they lie in the plane, then those n tuples are said to be solutions to this equation. In other words, this hyperplane equation. Okay, so I'll stop there for this session.